So we have derived the effective attraction between two electrons by electron-phonon coupling last time. So today we will start a new chapter, which is the final part of our course, which is the BCS theory of superconductivity for ordinary metals. And as you know already, the superconductivity was discovered in 1911 in mercury by Onnes in Leiden University in Netherlands. And the two main characters showing the superconductivity are as follows. The first, the resistivity drops to zero below critical temperature Tc, which is what we call them superconducting. And because there's no resistance, resistivity drops to zero, which means that there's some supercurrent flowing, right? So we know that all the conventional conductors in normal temperatures, when they carry charge current, there must be dissipation or some kind of energy lost. But since we don't have any resistivity in the superconducting state, this is the perfect conductor. But the Tc is really low, of order of 1 Kelvin. So you need to really lower the temperature to a single digit in Kelvin to see the superconducting state. This is not practical, but this is another issue to be worried about. The second important features of a superconductivity is Meissner effect, okay, which shows that this state is actually the perfect diamagnet. So we all learned that all this solid-state materials show some sort of diamagnetism, meaning if you apply the field to that system and there is the kind of induced flux which will compensate this change of your magnetic flux that you introduced initially. But the superconductor in the superconducting state is actually the perfect, shows perfect diamagnetism. So for temperature higher than Tc, if you apply the magnetic flux in the superconductor, so the magnetic flux will penetrate through this superconductor, the normal state of the superconductor or normal metal, so that there is some magnetic flux penetrating into the system. However, if you are below Tc and the system becomes a superconducting state, then if you apply the magnetic field, weak magnetic field, not strong enough, then the magnetic flux will not penetrate. Okay, so the system will create the magnetization to actually, cancel the external magnetic flux that you introduce. Okay, so there's no net H field inside the superconductor, and the magnetic flux that you inject in your system is actually repelled perfectly by the superconductor. So there is no chance, almost no chance, that the flux will penetrate into the superconducting state. And that magnetism is actually perfect. Okay? So a perfect conductor or superconductor is also a perfect diamagnet. Okay? So we'll see later that this Meissner effect is actually more fundamental than the zero resistivity in the superconducting state. And we note there are two classes or two types of superconductors that we can find for ordinary metals. One type is called type 1, where you get a perfect Meissner effect or perfect diamagnetism in a field for T below Tc. And this minus M, or minus magnetization, that the system induces due to the applied B field, as a function of a B field, shows this kind of linear relations for the field below the critical field. For the field above the critical field, then the superconducting state is totally destroyed, so the system becomes a normal metal. This is type 1, but there's another type called type 2 superconductor, where you have partial penetration of a magnetic flux into the system, and this magnetic flux form triangular lattice, which we call this Abrikosov vortex lattice, which was first introduced by Abrikosov a long time ago. And this H field as a function of temperature shows intermediate region where you have partial flux penetrating into the system like this. Okay, so the magnetization does not vanish above HC1, but there is a region, a window between HC1 and HC2 that this magnetization is still there, still finite. But below the HC1, you get a perfect diamagnetism. So that's called type 2 superconductors. And there's a third feature of the superconductor, which shows in the heat capacity or specific heat. Remember, the specific heat of ordinary metals goes like a linear in T and T cubic by phonon. Okay, so linear in T in this heat capacity comes from the electronic contributions, and the T cubic term comes from phonon. Remember that. So that's normal metal, but in the superconducting state, where T below Tc, so this the heat capacity divided by temperature goes like a jump first, and then exponential decay as temperature is further reduced. So the exponential decay of the specific heat coefficient indicates that there is a gap. And we'll see later that this gap is actually a spin gap. And this feature is a jump right at Tc and then followed by the exponential decay is a characteristic of a superconductor in the superconducting state. So the final feature of the superconductor is so-called isotope effect, okay, which means that this Tc, which is the critical temperature or transition temperature, times the mass of ions to the power of alpha is actually a constant. So m to the power of alpha times Tc is roughly speaking a constant. Okay, so this alpha ranges from 0 to 0.5, and Tc is actually constant divided by m to the power of alpha. So this is just an empirical formula. The heavier the atoms, the lower the Tc. So you can see this relation inversely proportional to each other is Tc and m to the power of alpha. Okay, so as I mentioned last time, the origin of this kind of very peculiar properties of electrons in metals come from the pairings between electrons, mediated by electron-phonon coupling. Okay, so let's take a short break. When we come back, we will introduce the phenomenological model to actually describe such properties in an empirical way, and then we will introduce formally, the quantum mechanical mechanism to form Cooper pairs between two electrons, mediated by the electron-phonon coupling. Okay, so let's take a short break. Let's continue. We could understand semi-classically or phenomenologically the superconducting behavior from this so-called phenomenological model, which is based on some kind of semi-classical treatment of this superconducting phenomenology. Okay, so under such a model, we could imagine that for finite temperature, T below Tc, finite temperature, we may have some normal current where the resistivity is finite and there's some collisions between electrons. And there's also a component called supercurrent where there's no such a collision, which leads to the zero resistivity. So both type of currents or electrons exist at finite temperature. And for normal current, we could estimate the velocity of this normal current from this semi-classical or classical Newtonian mechanics that this is given by charge E times electric field times lifetime divided by m, electron mass, which means that there exists some electric field which lead to the kind of collisions between electrons, and that leads to the finite lifetime of electron motion in the supercurrent. And we can imagine that this charge is actually effective charge E star, which we will see that this E star is actually 2 electron charge, okay, because of Cooper pairing, and m star, which is effective electron mass, and there's a density ns. In such a supercurrent state, this current density superflow Js vector is given by minus the density of a super current or charge in the superconducting state times the E star times the velocity. And because there is no resistance or no dissipation, the electrons may follow this Newtonian mechanics, namely F equals to ma, and we can see that this m star is the electron mass in the superconducting state, and dv dt is the acceleration of that electron in the supercurrent state, which is given by the force. Okay, the force is minus E star times electric field. So this is a Newtonian way of understanding this supercurrent. So if you take the differentiation of Js respect to time, you get simply this electric field E multiplied by some constant prefactor. And this will become very important later on to derive so-called the London equation. You could borrow the Maxwell equation here to derive the London equation. So from Maxwell equation, you know that the curl of E is given by minus 1 over c partial b partial t, and b is actually curl of A. So you have this form that curl of E plus dA dt divided by c is actually 0. So that's one of the Maxwell equation. And you could take the curl of this stuff, and you can replace this electric field E by this time derivative of the supercurrent. So E is given by this prefactor in the denominator multiplied by dJs dt. So if I simply just plug in the electric field over there in a supercurrent state, then we could show that this partial t times this stuff in the bracket vanishes, which means that this curl of this something inside the bracket is a constant of time. And London proposed that the stuff in the bracket Js plus this prefactor times vector potential A should vanish in order to satisfy the Meissner effect. And this is the famous London equation, which tells us that this supercurrent vector Js is given by minus this prefactor times the vector potential A, which is to say that the supercurrent is proportional linearly to the vector potential A. And we could use that London equation to derive the Meissner effect, because from this Maxwell equation, curl of B is given by 4 pi over c times this current J, and B is actually curl of A, and from London equation, Js is given by this vector potential A times prefactor with a minus sign. So you plug in this, you take the curl of a curve of B, and by using this London equation, and we could derive this relation that this Laplacian of B, the magnetic field, is given by the prefactor, constant prefactor times the field itself, and we define this prefactor as 1 over square of a London penetration depth, with lambda L is given by the square root of this constant prefactor, and which means that once we are in the superconducting state, we should satisfy this Laplacian equation for magnetic field. So if you solve this equation for this particular case where in the left-hand side of X, you have a superconductor, and the magnetic field that you apply to the system points to the y direction, and you can show that the field strengths decay exponentially inside the superconductor. This is outside. So you apply the field everywhere along the y direction, but if you calculate the field strength along the y direction, the magnitude of the field along the y direction and inside the superconductor, so you see that the B field inside the superconductor decays very fast, exponentially, but there is still a little bit leakage of this flux or magnetic flux penetrating into the system, but that penetration depth is really tiny for a superconductor. So roughly speaking, you can still consider that the superconductor repels all this magnetic flux, preventing the flux penetrating into the system. And this is precisely the Meissner effect is telling us. Once we have such a London equation, and we can show that the magnetic field cannot penetrate too deep inside the superconductor. It may penetrate just a little bit by a distance lambda L, and this lambda L for different metals behave slightly different, but it is order of, say, a few hundred nanometers. So this is really, really tiny penetration depth. So the magnetic field can penetrate slightly inside the superconductor, but it cannot just stay there, all the way to the middle of the superconductor, because it will decay very fast. And above lambda L, you don't see almost no magnetic flux. So that is precisely the Meissner effect. Meissner effect comes from the London equation, and the London equation could be derived from the semi-classical treatment of a supercurrent state. Okay, so this is just a phenomenology of superconductivity in ordinary metals. And next time, we will derive the Cooper pairs and from the more quantum mechanical treatment. Of course, it is related to the London equation. So the London equation is the most important phenomenological equation for superconductivity. Okay, so let's stop for now, and next time we will derive the pairing between two electrons based on this Meissner effect and London equation. Okay, so before the end of our lecture today, let me just argue from the London equation and canonical momentum of supercharged particles will lead to the Cooper pairs between two electrons. So remember from the classical mechanics and EMM, the canonical momentum P in the presence of a vector potential is given by m star times v velocity plus this vector potential A multiplied by minus E star over C. So we could take this supercurrent definition, which is minus ns times E star times velocity, and you could actually convert the velocity in terms of momentum and vector potential in such a expression here. But we know that, from London equation, that the supercurrent vector is given by this minus this prefactor times vector potential A. So you can combine these two relations, and you immediately see that the canonical momentum vanishes. So there's no net momentum remains in the superconducting state when you consider the electron pairings. So as we already pointed out last time, that two electrons get attracted to each other because of electron-photon coupling, and these two electrons should carry no net momentum, which means that P1 of electron 1 momentum plus P2, which is momentum of electron number 2, when you sum up this two momentum vector, you should get 0. And that's exactly what happened when we consider Cooper pairs of two electrons. These two electrons are very close to the Fermi surface, carrying opposite momentum. One is plus kF roughly, and another is minus kF. Okay? We'll see next time that these two electrons also carry opposite spins. Okay? So the two electrons carry opposite momentum near the Fermi surface will form Cooper pairs, and which follows from this London equation, and also definition of canonical momentum. Okay, so this derivation reassured that this Cooper pairs are made of two electrons carrying opposite momentum. So that is precisely what we will discuss next time. These two electrons form Cooper pairs, and next time we will see that the spins of these two Cooper pair electrons should also be antiparallel to each other. Okay, so that's the final remark. So next time we will start to construct the Hamiltonian to describe such a Cooper pairing in the superconducting state. Okay, so I'll see you next time.